Okay, here we've got another work question involving a slingshot. Val has got a new slingshot and she loads it up, and with an average force of 100 newtons, she pulls it back 30 centimeters. So from its resting position where there's no elastic energy involved, the elastic is just loose, she pulls it back 30 centimeters, that's her distance, and she must exert a force to the right to do that, according to my picture. Now we know that work is force times distance, and in this case, both are in the same direction once again. So the force she applies on average is 100 newtons, and that acts over a distance of 30 centimeters. Now we need meters to get the proper joule calculation. So I'm going to convert that to 0.30 meters. I'm going to check to make sure they're both parallel to one another, which they are, because that's the criteria to have work. And when I go 100 times 0.3 meters, I end up with 30 joules of work was done, and they're in the same direction, so that's positive work. So in other words, she's somehow loaded that slingshot with 30 joules of energy. Now we call that potential energy because that energy gets stored in the elastic band of the slingshot. So she's loaded this thing with energy potential. The work she does went into changing that slingshot's potential energy. So it's all potential energy. Once she releases it, then whatever's in that slingshot, that potential energy is going to then get converted to kinetic as that slingshot projectile gets launched. The other thing I want to just make a note of, it says average force. And that's important when you do the work calculation. If you'll recall from dynamics, it's easier to change the length of a spring or an elastic initially, and then it gets harder and harder and harder as the change in length gets greater and greater and greater. So on average, she's exerting a force of 100 newtons. Her final force should be greater than that. Her initial force would be much less than that, but on average, it's 100 newtons.